Today we are going to talk a little bit more about graphs of functions. By the end of this video, you should be able to describe the multiplicity of zeros for a function, and you should be able to describe the end behavior for a function. First, let's talk a little bit about polynomials. You should be somewhat familiar with them from Algebra 2. The graphs of polynomial functions are always continuous, smooth curves. So one example of a polynomial graph would be something like this. This is a polynomial. A discontinuous function, like this piecewise function here, would not be a polynomial because there is a jump. Another non-example of a polynomial would be a function like this. This one is also not a polynomial. First, it has a sharp turn. Second, it has a hole. So polynomial functions are always continuous, smooth curves. Let's take a look at zeros of a function. Other words for zeros are roots, solutions, and x-intercepts. So here we have a polynomial. There are a few things that I want to talk about with regards to the zeros of this polynomial. First, this zero here, since the graph goes straight through the x-axis, this one probably has a multiplicity of 1. Because the graph goes straight through the x-axis. This zero here, since it touches the x-axis but does not cross it, we know has an even multiplicity. And its multiplicity is probably 2. Perhaps it is an even number larger than that. The reason we know that this is an even multiplicity is because if you think about the graph of y equals x squared, it touches the x-axis but does not cross it. So, even multiplicity touches the x-axis. If we look at the next zero here, the graph kind of curves through the x-axis. It does cross the x-axis, but it's not in a straight line like this first zero. So this zero definitely has an odd multiplicity because it goes through the x-axis. It crosses the x-axis. And since it kind of curves through, its multiplicity is probably 3, perhaps more. If we think about the graph of y equals x cubed, we know that that graph curves through the x-axis. So one thing to remember is that roots with odd multiplicity cross the x-axis. Now, if we look at the last 0, this one, the graph goes straight through the x-axis. So since it crosses the x-axis, we know for sure that this root has an odd multiplicity, and it is probably 1. The last thing I want to mention is degree of a function. If you remember from Algebra 2, if you are looking at the equation, the degree is the highest exponent of x. If you're looking at a graph and you add up all of the multiplicities, that will give you the minimum degree. So, if we look at this graph, we have a multiplicity of 1, multiplicity of 2, multiplicity of 3, and another multiplicity of 1. So if I add up 1 plus 2 plus 3 plus 1, I get 7. So this is probably a graph of a 7th degree polynomial, but it could be a higher degree polynomial. So the degree for this one is at least 7. So let's take a look at this function. We have f of x equals 5 times x minus 2 times x plus 3 squared times x minus 5 cubed. From this, I can determine that the zeros of this function are x equals 2, x equals negative 3, and x equals positive 5. And I get all of these zeros from setting each of the factors equal to 0. Now when we're looking at the equation, the multiplicity is the exponent on each of the factors. So x equals 2 has a multiplicity of 1, x equals negative 3 has a multiplicity of 2, and x equals 5 has a multiplicity of 3. Since x equals 2 and x equals 5 both have odd multiplicities, we know that the graph is going to cross the x-axis at those points. And since x equals negative 3 has a multiplicity of 2, which is even, we know that the graph is going to touch the x-axis at that point. A couple of other things that we can find. We can find the y-intercept. We can do this by plugging 0 in for x. So f of 0 is 5 times negative 2 times 3 squared times negative 5 cubed, which if you plug that in your calculator, you end up with 11,250 as our y-intercept. The last thing I want to mention before we sketch a graph of this function is power function. We can use this to approximate this graph. So we mentioned earlier that if you add up the multiplicities, you get the degree. So if I add up the multiplicities, I know that the degree is 6. So we can say for the power function that this function is approximately equal to the function 5x to the 6th. This 5 comes from the leading coefficient here. And that'll give us a general idea of some of the properties of this function. So now let's sketch a graph. So I know the graph is going to touch the x-axis at -3, then go through its y-intercept of 11,250. Then since it has a multiplicity of 1 at x equals 2, it's going to go straight through the x-axis. And at x equals 5, we have a multiplicity of 3, so the graph is going to curve through the x-axis. So if we sketch our graph, we have something like this. And that gives us an idea of what our graph would look like. Let's take a look at the next example. We have f of x equals x squared times x minus 2. So, first of all, we're going to start off with our zeros. If I set each of these factors equal to 0, I'll get x equals 0 and x equals 2. X equals 0 has a multiplicity of 2 because of this exponent here. X equals 2 has a multiplicity of 1. So I know that my graph is going to touch the x-axis at 0 and cross the x-axis at 2. Since 0 is one of my zeros, that means our y-intercept is also the point 0, 0. If I look at the power function, we know that the degree is the sum of the multiplicities, which is 3, and our leading coefficient is 1, so our power function is just x cubed. So now, let's sketch a graph. I touch the x-axis at 0 and cross the x-axis at 2. So our graph looks something like that. Now, you might be wondering why I drew my graph this way and not this way. Well, we'll get to that in 1 minute. Now, for a polynomial, we know that if f of x has a degree of n, it has at most n minus 1 turning points. And you'll learn more about that concept in calculus. Let's move on to end behavior. You might remember from Algebra 2 that you can determine the end behavior of a polynomial by knowing two things: the degree and the leading coefficient. So if we have an even degree and a positive leading coefficient, our graph will look something like this. Or at least that's the end behavior it'll have. Our end behavior will be as x approaches negative infinity or as x approaches positive infinity. F of x approaches positive infinity. If we have an even degree polynomial but a negative leading coefficient, our graph will look something like that. So our end behavior is as x approaches negative infinity and as x approaches positive infinity, f of x approaches negative infinity. If we, however, have an odd degree polynomial with a positive leading coefficient, our graph will look something like that. So as x approaches negative infinity, f of x approaches negative infinity. And as x approaches positive infinity, f of x approaches positive infinity. If we have an odd degree polynomial with a negative leading coefficient, our graph looks something like that. So the end behavior, as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches negative infinity. So end behavior can give us one extra piece of information as we are trying to sketch graphs of polynomials. Finally, let's try to sketch these two equations by hand. First, we have a of x equals x cubed plus x squared minus 12x. We need to find the zeros, and to do that, we need to factor this function. So first, I'm going to factor out a GCF of x. Then I'm going to factor this trinomial. Then if I set all of those factors equal to 0, I get that my zeros are x equals 0, x equals negative 4, and x equals positive 3. All three of these have a multiplicity of 1. Which means all of them are going to cross the x-axis. Since we know that x equals 0 is one of our x-intercepts, we know that our y-intercept is also 0, 0. Now, I can see that the leading coefficient is 1 and the degree is 3. So I have a positive leading coefficient and an odd degree, which means that my end behavior will be as x approaches negative infinity, a of x approaches negative infinity, and as x approaches positive infinity, a of x approaches positive infinity. From this, I can sketch my graph. So the graph crosses the x-axis at all three zeros, and I know that my end behavior will be something like this. So my graph will look approximately like this. For our last example, we have b of x equals 3x to the fourth minus 9x cubed minus 12x squared. I'm going to factor out my GCF of 3x squared. Then I'm going to factor my trinomial. If I set each of those factors equal to 0 and solve, I get that my zeros are x equals 0, x equals 4, and x equals negative 1. X equals 0 has a multiplicity of 2 because I was able to factor out an x squared. 4 and negative 1 have multiplicities of 1. This means that the graph will touch the x-axis at x equals 0 and cross it at 4 and negative 1. Since x equals 0 was one of my x-intercepts, I know that my y-intercept is also 0, 0. By looking at the original equation, I can see that my leading coefficient is positive and my degree is even, which means that my end behavior will be as x approaches both positive and negative infinity, b of x approaches positive infinity. And this is a shortcut way of writing the end behavior since both ends are going up. Now we can sketch our graph. So I have zeros at negative 1, 0, and 4. And I know that the end behavior says both ends of the function will be going up. So my function will look something like this.